Hello, in this video I'm going to give a very brief overview of Maxwell's equations. This is going to be really high level, so if you're not a regular to these videos and you've just stumbled across this and you're hoping for some rigorous analysis and discussion of Maxwell's equations, then this isn't really going to be for you. This is much more for just to give a taster of what they're about and why they're considered to be so important for people who haven't gone off to university and learnt the necessary maths that sit behind it all. Right, so yeah, Maxwell's equations, so named after James Clerk Maxwell, the mind-boggling genius Scottish physicist of the 19th century. So these were first formulated in 1861 after decades of work by numerous scientists. Maxwell was the one, though, who was able to pull all of this together. He initially came up with a set of 20 different equations with 20 variables in. And there were numerous formulations that came after that, notably with assistance. You had Oliver Heaviside, who he condensed these equations down into pretty much the four Maxwell's equations, give or take, that we deal with nowadays. But there are still multiple formulations. Although each one of these four Maxwell's equations has a description and a name associated with them, they can still be written in different ways depending on what it is we're actually trying to describe or analyze. So I'm just going to briefly go through those four, say what they are and roughly what they're getting at. So number one, we've got Gauss's law for electricity. So Gauss's law for electricity. So this is talking about, is describing electric fields associated with electric charges. So this is describing electric fields. So it's saying if you've got some kind of charge, whatever it may be, and you've got some region, some surface around this charge, then Gauss's law will be able to tell you how this electric field is behaving, what it's like, what its characteristics are. It just gives a description of the electric field around this particular charge. So that's what we're doing with Gauss's law for electricity, electric fields. The second one is we've then got Gauss's law for magnetism. Not surprisingly, we're going to have stuff for electricity, stuff for magnetism, because we are in electricity and magnetism. So Gauss's law for magnetism, this is doing more or less the same thing. He's saying, right, if you've got some magnetic charge, a magnetic dipole, part of the consequence of this is that there's no monopoles, there's no magnetic monopoles. So is one consequence of this. As in, you can't just get a north pole or a south pole, they always come in pairs, is one thing that Gauss's law for magnetism is telling us. But if you've got one of these magnetic dipoles, then it's going to do a similar thing to Gauss's law for electricity, but for magnetism. So this is for describing magnetic fields. Again, this is very broad brush. But now we've got our first two Maxwell's equations are describing electric fields and describing magnetic fields. Magnetic fields. Writing the wrong words there. Right, so that's our first two. Then we get on to things which are, how do electric fields and magnetic fields interact with each other? What is the relationship between the two of them? So third Maxwell's equations is Faraday's law. So this is Faraday's law of magnetic induction. So how does a changing magnetic field induce an electric field? So this is a description of that. So we've got a description of a changing magnetic field leads to a changing electric field. And we've seen a bit of Faraday's law, haven't we, when we were looking at electromagnetic induction and how this is how transformers are working and other such things. If you move a conductor in a magnetic field, or you move the magnetic field around a conductor, as long as you've got this relative motion between conductor and magnetic field, then you can induce an electric field, which then induces a current in that conductor. So we have looked a little bit at Faraday's law out of the 4 laws. So that's the third one. We've now got an interrelation between magnetic fields and electric fields. And then we get the Ampere-Maxwell law, which is just sort of finishing off the circle here, is completing the circle. This is describing of how a changing electric field induces a changing magnetic field. So we've got this continual interplay between the electric fields and the magnetic fields. And you can see why this is, it's obvious why this is also important. You know, all the way through these videos, we've been talking about how all of this description of electricity that we're building up and how electric current flows and how electromagnetic waves behave, it all depends upon this continual back and forth interaction between electric fields and magnetic fields. You move something that's got electric charge, it creates a magnetic field, and you get the changing magnetic field, you get the changing electric field, which creates a changing magnetic field. This is Maxwell's equations is just describing all of this in rigorous mathematical detail. So it's bringing all of it together. It's bringing electricity together with electric fields, magnetic fields, electromagnetic radiation, all of these things, which back in the past were considered to be separate. It's not immediately apparent that magnetism and electricity and light are all, just different aspects of the same phenomenon. That's in no way obvious, but Maxwell's equations show how they are. I mean, it's mind-boggling, really, when you bring all of these things, which are just so fundamental to everything that we do, and say, well, actually, we can describe in these 4 equations how actually they're all the same thing. I mean, it's mind-boggling. Although they're not simple equations to learn in terms of the maths and then applying them, this is undergraduate level maths and physics. But once you get into them, then the simplicity and how streamlined they are and how powerful they are to describe so much, it is mind-boggling, really. It's incredible. So yeah, this is why one of the greatest things ever created in science ever discovered is Maxwell's equations. Now, as I say, there are different ways of writing these things down. I mean, we've been talking in our videos about E fields and B fields, our electric fields and our magnetic fields. These are sort of foundational fields. These are the most foundational. I suppose they're the most universal, but they can also be quite unwieldy. So not all descriptions that we want to make of electricity and magnetism are going to be in terms of these particular fields, these E and B fields. So you start seeing descriptions as well, where you get D fields, H fields. So these are different formulations of Maxwell's equations, just for a different level of analysis. It can be easier to apply Maxwell's equations to larger scale macroscopic behavior if you're using D and H fields. They're a bit more intuitive, they're easier to apply, but they're not as foundational, and you have to require and apply, depend upon some experimentally determined parameters. So they're not as pure as a sort of foundational E and B field descriptions and formulations of Maxwell's equations, but you can write them out in D's and H's, and there's other fields as well. I mean, it's not just those. And they can be easier to use, but then they're not quite as pure in their description. So yeah, that's just a real high level view of what Maxwell's equations are about and why they're so important. As I say, that descriptive power of so many different things that weren't obviously different aspects of the same phenomenon is one of the greatest breakthroughs in all of science history. So hopefully that just gives you a flavour of what they're about. If you go off to study physics at university, you'll be studying Maxwell's equations probably in your first year undergraduate. I mean, that was certainly when I came across them for the first time, so I'd imagine they're still going to be first year undergraduate, second year at the latest, I would have thought. So yeah, you'll have all of this fun in front of you when you come across them. They can be quite intimidating when you first start learning them. It can be easy to you can't see the wood for the trees. Sometimes you have to get so down into the weeds of learning the details of exactly what the equations mean, but just make sure you don't lose the bigger picture, sight of that, of just how much power you're going to have. It's quite the string to your bow if you can understand Maxwell's equations and apply them successfully.